Student, screen is visible. Screen is visible.
Yes, sir.
Okay. Okay. Yesterday we were discussing with Joule's experiment, and so while explaining the Joule's experiment, you have to draw these two diagrams. Okay, one is a closed system undergoing in a cyclic process, and this is the PV diagram. Okay, and according to the first law, cyclic integral of dq is proportional to cyclic integral of dt. Suppose you are putting in mathematical form, we can write cyclic integral of dq equals to j into cyclic integral of dw, where j is the Joule's equivalent of heat. Okay, and another one, okay, that is the first law of thermodynamics for a closed system undergoing a non-cyclic process. Okay, whatever the Joule's experiment illustrate for closed system in a cyclic process. Now we are dealing with the closed system undergoing a non-cyclic process. Okay, so already you studied cyclic process and non-cyclic process. Cyclic process is one where the initial and final states are identical. Okay, so here in case of non-cyclic process, the initial state and final states are identical. Okay, so first point, if a system undergoes change of state during which both heat transfer and work transfer are involved, then the net transfer will be stored or accumulated within the system. Okay, as I said, this first law of thermodynamics mainly deals with the energy interaction. Energy neither created nor destroyed. We can take the heat into the system and work from the system, or work into the system, or the heat from the system. Like that, the heat and work interaction takes place between system and surroundings. Okay, and the whatever the net energy is, okay, you see this diagram. So here q is taken as input to the system and w as output to the system. Okay, if any one of is not there, it does not hold good. First of thermodynamics, you remember, suppose I don't have w, in that case it does not holds good the first law of thermodynamics. In order to explain the first law of thermodynamics, we should have the two modes of the energy transfer. Okay, so we can take heat into the system and w from the system. On the other hand, we can take w into the system and q from the system. If any one of the energy transfer is not there, in that case it does not holds good the first law of thermodynamics. Okay, whatever now I am explaining, it is a non-cyclic process. Non-cyclic process means where the initial and final states are identical but related to closed system. Okay, closed system means the system of fixed mass. As we studied in first chapter, closed system is one in which it is a system of fixed mass. Only the energy interaction takes place between system and surrounding. Same concept we are applying here also. Okay, here as you see in the diagram, the Q, the heat transfer is taken into the system, and W, that is the work transfer from the system, and the net energy, that is according to the first law of thermodynamics, Q equals to W. Okay, suppose if we are going to express in net energy transfer, we can write it as Q minus W, that is a net work transfer. Whatever the net work transfer in the system is a form of energy, and it is neither heat energy nor work energy. Okay, you remember, whatever the net energy accumulated in the system is a form of energy, but it is neither work energy nor the heat energy, but it is a sort of energy. We are calling this energy as internal energy, and we are going to represent by symbol delta E. Okay, so Q minus W equals to delta E. So where Q is the heat transfer into the system, W is work done by the system, and the net energy Q minus W is equals to some sort of energy that is represented by symbol delta E, or sometimes delta U also. Okay, you can use either capital E or capital U. Okay, so both are same meaning. Delta is called as the increase in the energy of the system. Okay, as you add the heat into the system, obviously there will be increase in the energy of the system. Okay, as you can take the heat from the system, there will be a decrease in the energy of the system. Okay, so the whatever the energy stored in the system is neither work energy nor heat energy. It is a form of energy and represented by symbol delta E. Okay, where delta is called as internal energy of the system. Okay, and you remember then what is the sort of internal energy? Internal energy is summation of kinetic energy, potential energy, as we studied in first chapter, that is the microscopic and macroscopic approaches. Macroscopic properties are pressure, volume, and temperature. Okay, here the internal energy deals with related to microscopic energy, like kinetic energy of molecules, potential energy of the molecules. That delta is nothing but it is a summation of kinetic energy, the potential energy of molecules. Okay, just you remember. And delta E is E2 minus E1. You remember, E2 is final internal energy minus E1 is initial internal energy. Delta E is E2 minus E1. Okay. You remember it's a very simplest formula you have to use in the numerical problem. Q minus W equals to delta E. The meaning of delta E is E2 minus E1. Whatever there, always you have to take a final state minus initial state. Okay, don't take initial to final. You have to take always from final to initial, because we are integrating integration of TV is V2 minus V1, like that. Same thing here also. Delta E is E2 minus E1. Okay, you remember this formula to solve the problem. And here, suppose you see the second diagram, if there are more energy transfer takes place. Okay, you see a W1 is entered into the system and Q1 is the heat transfer from the system. You see this diagram. So there are more than one energy transfer takes place in a closed system. Okay, whatever I explained, it is only related to only one mode of heat transfer. In a system, sometimes there may be more than energy transfer also. Okay, here W1 is the work done on the system and Q1 is the heat transfer from the system. Okay, and we are having one more. Okay, Q2 is the heat transfer into the system and W2 is the work done by the system. And related to 3, okay, Q3 is heat taken into the system and W3 is the work done by the system. Okay, and W4 is work done on the system and Q4 is the heat transfer from the system. Like that, we can take any number of the things. Then how to write? Okay, as according to the first law of thermodynamics, the summation of heat transfer equals to the summation of work transfer. Okay, and already you know the sign convention for heat transfer and work done. Okay, so whenever the heat is taken from the system, you are going to represent it as minus. Okay, so you can add like this: minus Q1, that is sign convention is minus Q1 plus Q2 plus Q3. Okay? So you can write equate equals to, that is according to the first law of thermodynamics, the summation of heat transfer, that is minus Q1. Don't take plus, because the heat is taken from the system, minus Q1 plus Q2, heat added to the system, plus Q3. This is the net heat transfer equals to the net work done by the system. Then you see the arrow mark. Okay, W1 is into the system, means it is the work done on the system. You have to take minus W1 plus W2, next plus W3 minus W4. Like that you can write. Okay, so you can write, you can take any number of energy transfer, but the total energy associated with the system remains constant. That is, summation of the heat transfer is directly proportional to the summation of the work transfer, because the energy it depends upon the law of conservation of energy. So how we are going to write? Minus Q1 plus Q2 plus Q3 equals to minus W1 plus W2 plus W3 and minus W. Okay, this is the more than one energy transfer involved in the system. Okay, next important. Okay, every time they used to ask this derivation. Okay, it's a simple derivation. Okay, we have to understand properly. And this question carries 8 marks. Okay, in the exam they'll ask, prove that internal energy is property of the system. Okay. It's not energy, this is the internal energy. Okay. Okay, before starting the derivation, you have to draw the PV diagram. Okay, so one is X is V and Y is P diagram, that is PV coordinates diagrams. And then you have to draw this diagram. Okay, so here once again we can tell it as a cyclic process. Cyclic process means the initial and final conditions are identical. Okay, so let us consider a system undergoing in a cyclic process. Okay, so here you see, first I am going to take point 1. So, and after certain process, okay, it may be any process, it reaches state 2 by following path A, okay, and then returns from state 2 to state 1 by following path B. Now we consider only the paths A and B. Okay, so 1 and 2 are thermodynamic state points, as I said. So the point functions and path functions, all the thermodynamic properties are point functions, and all the energy interactions like work transfer, heat transfer are path functions. Okay, and point functions are exact differential, path functions are inexact differential. Okay, so in order to prove internal energy is a property of the system, okay, you have to draw this diagram. So without diagram you can't derive. This diagram is most important. Okay, now I am taking state 1 and it reaches state 2 by following path A. Okay, then it returns back from state 2 to state 1 by following path B. Okay, now second time what I am going to do, so it starts from state point 1, reaches the state point 2 by following path A. Then instead of following path B, it follows the path C. Okay, there are two things you have to consider. First, you consider 1 to 2 by A, and then 2 to 1 by B. Second time, you consider 1 to 2 by path A, and then 2 to 1 by following path C. Okay. Now, I am taking the process state 1 to state 2 by process A. Okay, and from state 2 to state 1 by following path B. Okay. Now, we studied that for a cyclic process, the summation of heat transfer is exactly equals to the summation of the work transfer, as we studied in the previous class. Okay. Same thing you apply. Okay. Now, for the process 1, 2, B1A, 2, B1. Now, we consider only this upper part. Okay. 1A, 2, B1. Okay, this is the cyclic process. Okay, then cyclic integral of dq for 1a to b1. You see the equation here. Cyclic integral of 1a to b1 is equals to cyclic integral of dw. That is 1a to b1. Okay, just you apply the formula. Just in the subscript, you can write it as 1a to b1. Here also you can write 1a to b1, because first time I am considering this cyclic process 1a to b1. It is cyclic integral of dq for the process, for the cyclic process 1a to b1 is equals to cyclic integral of dw for the path, that is same thing, 1a to b1. Now, now, so there are two work transfer and the two heat transfer. Okay, summation of dq means what? Okay, so cyclic integral of dq is not nothing but the summation of the two heat transfer. That is whatever the q1 to 2 plus q2 to 1. Okay, because we are having the two paths. Okay, so cyclic integral of dq, that is summation of heat transfer, is exactly equals to the heat transfer during process 1 to 2, and then plus the heat transfer during the process 2 to 1. Okay, same thing we can write here. Okay, you have to split cyclic integral of cyclic integral means what? It is a summation of heat transfer. Now we have to split this term into a two integral part. Okay, that is integration of dq for the process 1 to 2 for by following path A. You see this equation. Okay, plus integration of dq between the process 2 to 1. You see, first time you have to take 1 to 2 following path A. plus integration of dq for the process 2 to 1 by following path b. Okay, you have to split cyclic integral of dq into two terms. Okay, this is the LHS part. Okay. And during RHS part, how we are going to write? Same thing you have to write. That is integration of dw for the process 1 to 2 by following path A. Okay, see this equation? Integration of dw for the process 1 to 2 by following path A plus integration of dw, okay, between the process 2 to 1. Okay, don't write 1 to 2 here, you have to write 2 to 1 by following path B. Okay, so first step is you have to write the first law of thermodynamics, and then you have to split into the parts into two separate processes. Okay, first I am writing for entire cyclic process, and in this step I am going to split into two processes and writing the equation, that is integration of dq for the process 1 to 2 by following path A plus integration of dq for the process 2 to 1 by following path B equals to the integration of dw for the process 1 to 2 by following path A. Okay. Then plus integration of dw for the process 2 to 1 by following path B. Okay, you call it as equation number 1. Okay, now consider the cyclic process. Okay, now you call it as equation number 1. Okay, now consider this a 1a 2b1 is one cyclic process. In the next step, what I am going to do, I am not going to consider this path B. Instead of path B, I am going to consider the path C. Hence, we are having the two cyclic process in this diagram. One is 1a 2b1 and another cyclic process is 1a 2c1. Okay, first I consider 1a 2b1. Now I am going to consider the cyclic process 1b 2c1. Okay, can you tell anybody how to write this equation for 1b 2c1? Anybody? Okay, how you are writing for the process 1a 2b1 in equation number 1? Same thing you have to write in equation number 2 also. Instead of path B, so you have to write uh, A and C. Okay, so now in the second case B is not there, only A and C are there. Okay, then how you are going to write? Integration of cyclic integral of dq equals to cyclic integral of dw. You see the equation number 2 here, that is integration of dq for the process 1 to 2 by following path A. Okay, this equation plus integration of dq. First you take dq, integration of dq for the process 2 to 1 by following path C. Okay, now in the second case, I'm not considering B, I'm considering only A and C, 1A to C1 as a cyclic process. Summation of heat transfer equals to the summation of work transfer in any cyclic process. Now we have to split that cyclic process into individual process, that is integration of dq for the process 1 to 2 by following path A plus integration of dq for the process 2 to 1 by following path C. Okay, you should be very careful in writing the notation A, B, C. Okay, equals to the integration of dw by following path A. Okay, don't take B. Integration of dw between the process 1 to 2 by following path A plus integration of dw for the path 2 to 1 following the path C. Okay, now we call it as equation number 2. First, just you write cyclic process and then just you split into two parts. Okay. Now, I am going to subtract equation number 2 from 1. Okay. So what you are going to get? Okay, I am going to subtract equation number 2 from 1. Okay. So what are the common terms gets cancelled? That is this one and this one gets cancelled. Okay, I'm going to subtract equation 2 minus equation number 1. That's it. Okay, equation number 2 minus equation number 1. That is the first term gets cancelled. Okay, because these are the common term. This gets cancelled. Okay, then how we are going to write? Okay, integration of dq for the process d. Just it is equation number 1 minus 2. Sorry, it is equation number 1 minus 2. 1 minus 2 means that is first term gets cancelled because we are having the common terms in both the equation. Then this term is different. How we are going to write? Integration of dq between the process 1 to 2 following path uh, b. Okay. So integration of dq between the process 2 to 1 by following path b minus of this equation. Okay, equation number 1 minus 2 means this first term gets cancelled. You have to write the second term integration of dq 2 to 1 by following path b minus of integration of dq by following path c equals to, now you write the right hand side equation. Right hand side equation, what are the common terms? This third term is common. Now you cancel this third term, and then fourth term you can write like this: integration of dw between the process between the state points 2 to 1 by following path b minus of integration of 2 to 1 dw minus this is c. Okay, by following path c. Just first you write this cyclic process, then you split into two process for cyclic process 1 to 1a to b1. In the second case, you take the cyclic process 1a to c1, don't take b, split into two parts, then you call those equations as 1 and 2. Just equation number 1 and 2 you can write. Now so here you can write integration of dq is common. Okay, so you take the common term. Okay, here 2 to 1, 2 to 1 by following path b. Okay, is there it is common term? What you can write? Integration of dq minus dw for the following path b. Okay, now rearrange the term. That's it. The last step what you are seeing is rearrangement of term. That is integration of dq minus of integration of dw. Just you shift this term towards LHS side. Okay, integration of dq minus dw between the limits 2 to 1. Okay, in the limits 2 to 1 by following path b. Now you write the right hand term. Okay, you make q and w one side and q and w other side. Okay, just you rearrange the term. That is integration of dq minus integration of dw. You shift this third term towards LHS side equals to the integration of, you take this term, that is second term, towards right hand side. That is equals to the integration of dq minus of integration of dw between the limits 2 to 1 by following path c. Okay, so you rearrange the term. Okay, okay. But what about q minus w? Q minus w is nothing but what we studied in the previous class, that q minus w is delta E. Okay, here once again we are having a term called as q minus w by following path B. Okay, so we can write, so delta EB equals to delta EC. Integration of dq minus dw is nothing but what? Delta EB, because following the path B, and equals to delta EC. Because we know that q minus w is delta E. So same thing you have to apply and write for the paths B and C. That is delta EB equals to delta EC. Okay. So whatever process you take, there is no change in internal energy. Okay, so in the first case I took this one 2 by following path A. So delta EA equals to delta EB, that is equals to delta EC. So whatever the process may follow the path, there is no change in internal energy of the system. So we can conclude that delta EA equals to delta EB equals to delta EC. So whatever process you take, so there is no change in internal energy of the system. Okay, delta EB equals to delta EC. Like that, you can write for delta EA equals to delta EB. Okay, because there is no change in internal energy. Okay. So hence, we can prove that the internal energy is a property of the system. Don't make confusion between the heat transfer, work transfer, and internal energy. The internal energy is a energy which is a sort of energy stored within the system. It is neither work energy nor the heat energy, but it is the energy associated with the system. Like other properties, pressure and temperature, how we are having the definite values, like that, this internal energy is also having a definite value. Hence, as we studied that all the thermodynamic properties are the point function, like that, this internal energy is also a property. Okay, it is not a path function, it is a point function. Okay, hence from this equation, it is clear that the internal energy is a property of the system. Okay, and hence it is so we can write delta E as E2 minus E1, but we cannot write integration of dq as q2 minus v1 wrong. But we can write delta E, that is nothing but the change in internal energy from higher value to lower value, E2 minus E1 or U2 minus U1. Okay. Understood this derivation, guys? Any doubts in this derivation? So this is one of the important derivation in first law of thermodynamics. Okay, you have to try to understand this derivation. Any doubts? Okay. So this derivation, internal energy. Any doubts? Anyone having any doubts? Internal energy. Okay.
No, sir.
Uh, because one of the important concept, once you understand this concept, then it is easy to understand the other concept, like second law of thermodynamics will be very easy. That's why this is the most important concept. Okay, how the first law of thermodynamics, we are having a new term called as internal energy. Like that, we are having a term called as entropy in second law of thermodynamics. First law of thermodynamics leads to a new term called as internal energy. On the other hand, the second law of thermodynamics leads to a new concept called as entropy. You are having second law of thermodynamics and entropy in third module. Once again, those are the two important chapters in thermodynamics. That's why the understanding of the internal energy concept is most important. Okay. Okay, I'll explain one more concept called as the perpetual motion of first kind. Okay, we are having one more concept called as perpetual motion machine.
Sir,
Tell me.
so in cyclic process, internal energy is zero, sir.
Cyclic integral of dq is zero, correct. Cyclic integral of d is also zero. Okay, because internal energy is a property, not a path function. So you remember the cyclic integral of any property is zero. Like cyclic integral of dq is zero, cyclic integral of dw is equals to zero. Whenever you are taking in a cyclic process, it will be zero. Okay, suppose you're not taking in a non-cyclic process, it will not be zero. Understood? Okay.
Okay.
Because you remember cyclic integral of any property. Okay, cyclic integral of dq equals to zero, cyclic integral of dw equals to zero. Sorry, cyclic integral of du equals to zero, cyclic integral of dt equals to zero. Like that, just now we proved internal energy is a property. Hence, as per our definition, cyclic integral of any property is 0. So hence, cyclic integral of dE is also 0. Okay. Next concept is this also one of the important concept called as perpetual motion of first kind. Okay, so every time they used to ask, you remember these are the three important things they used to ask in the exam. One is Joule's experiment to illustrate first law of thermodynamics. Second part is to prove the internal energy is a property of the system, and third part is what I am explaining now, that is perpetual motion of first kind, or it is also called as PMM1. Okay, PMM means perpetual motion machine of first kind. Okay, as I said, first law of thermodynamics mainly depends upon the and law of conservation of the energy. We can take the energy in or heat energy as input to the system and work energy as output of the system, or we can take the W as input to the system and Q as the output of the system. If any one of the energy transfer is not there, in that case, it does not holds good the first law of thermodynamics. That is called as perpetual motion of first kind. Means any system or any machine which violates the first law of thermodynamics is called as perpetual motion machine of first kind. Okay, so you see the first diagram. Okay, it is impossible to construct a perpetual machine of first kind. It is imaginary in nature. Okay, we don't have the exact perpetual motion machine of first kind because it violates the first law of thermodynamics. Okay, you see the first diagram. Okay, here there is a continuous work done by the engine. Okay, but without input to the heat transfer. Okay, so that it violates the internal energy. It violates the first law of thermodynamics. Okay, so as I said, in order to extract the work continuously from the engine, we have to supply the equal amount of the heat transfer to the system. Then only we can extract the work energy. If heat transfer is not there, in that case, so it is not possible to extract continuously work from the engine. Hence, it violates the first law of thermodynamics. Suppose Q is not there, that is summation of the Q is 0. But we are having equals to summation of W. It is not holds good. According to first law of thermodynamics, it does not hold good. Hence, such kind of machine is not possible, because in order to extract the work continuously from the system, there will be continuous supply of the heat to the system. Then only this engine works. Suppose if heat transfer is not there and you are going to extract work continuously from the engine, it is not possible. Hence, it violates the first law of thermodynamics. It violates the first law of thermodynamics. Such kind of machine, we are calling it as PMM1, and PMM is not possible at all, and it is a virtual machine or imaginary machine. Okay, you see the second diagram. Okay, here what it is there, here we are going to supply continuously work to the machine. You see the arrow mark. So in the second diagram, we are going to supply the continuously work to the machine, and there is no heat transfer at all, because you see the dotted line. Dotted line means no heat transfer. Okay. Here also in the second diagram, dotted line indicates there is no heat transfer at all. There is only the continuous supply of the work without extracting the heat from the machine. In that case, whatever the work you are going to supply, just it accumulates within the machine, and it's not possible to transfer the heat from the machine. Okay. So as we said, okay, in Joule's experiment, whatever the amount of the work done on the system is exactly equals to the amount of the heat transfer from the system, and only it holds good. Okay, such a imaginary machine is called as PMM1. So you have to explain PMM1 is a imaginary machine. It is not possible to construct perpetual motion machine of first kind. Okay, so in first case, it is the one in which we can do continuous work without receiving the heat energy from the surroundings to the system. And in the second diagram, it continuously consumed the work without extraction of the heat from the system. Okay, it may be engine or it may be machine. We are going to study the heat engine in second of thermodynamics. I'll explain clearly what is the engine, what is the machine, everything. Okay, just you consider engine as a system, and in the second diagram, machine as a thermodynamic system. Okay. Hence, the PMM1 is not possible at all. Okay, and it is imaginary machine. Okay, how we are having the internal energy concept and PMM1 concept in first law of thermodynamics. Like that, we are having the entropy and PMM2 in second law of thermodynamics. So try to understand PMM1. Okay, so PMM1 means in order to supply the heat continuously from the end, then only there will be continuous extraction of the work. Suppose if heat transfer is not there, there is no work transfer at all. Okay, and on the other hand, we should have the continuous extraction of the heat transfer from the machine with continuous supply of the work to the machine. Such a fictitious machine is called as the PMM1. PMM1 is not possible at all. Okay, remember, this is a imaginary machine because the PMMN violates the first law of thermodynamics. Okay. Next, I'm going to explain the internal energy. Okay. So we studied Q minus W equals to delta E, where Q is heat added to the system and W is the work done by the system. The net energy Q minus W equals to the change in internal energy, that is delta E. Okay. Now total energy that is given by E equals to mm, kinetic energy plus potential energy plus internal energy. Okay. So this, whenever you're considering a system, we are having the total energy associated with KE, PE, and IE. IE is internal energy. Okay. As I said, we are having the micro level energy and macroscopic level energy. Okay. The microscopic properties are pressure and temperature, and then this microscopic properties are our molecular energy, kinetic energy of molecules, potential energy of the molecules. Now we're having this concept now. Okay, total energy of the system is kinetic energy plus potential energy plus internal energy. As I said, internal energy is neither work energy nor heat energy, just it is the energy associated with the system. Okay. Now, suppose whenever you are writing in this one differential form, we can write d of E equals to d of Ke plus d of P plus du. Okay, this internal energy is represented by U, as I said, either capital E or U. Okay, and the first law of thermodynamics. Okay, as we know that Q minus W equals to delta E. Okay, and okay, so you can write okay, dq equals to q minus w equals to delta E, or q equals to w plus delta E. Same thing we can write in the differential form. Okay, don't make confusion. Whatever E here is the total energy, and whatever U indicates your the internal energy. Okay, and Q is nothing but Q minus W equals to delta E. Okay, so Q equals to delta U plus W. W means in the differential form dW. Only two things you have to take into consideration is kinetic energy plus potential energy. Okay. So this is the total energy. D equals to dKe plus dP plus du. Okay. And here this second equation related to only the first law of thermodynamics, that is Q equals to du plus dW, and you have to add this kinetic energy and potential energy of the molecules. Okay. Okay. So now I'll solve one simple numerical problem. Okay, as I said, you have to remember one simple equation, that is Q minus W equals to delta U. Okay. So you see the first problem, in a cyclic process, the heat temperatures are plus 14.7 kilojoules minus 25.2 kilojoules minus 3.5 kilojoules and plus 31.5 kilojoules. What is the net work done for this cyclic process? They are giving the 4 heat transfer, okay, and this one. What is the net work done? Okay, so very simple. So according to the first law of thermodynamics, cyclic integral of dq equals to cyclic integral of dw. Cyclic integral of dq is nothing but what? Q1 plus Q2 plus Q3 plus Q4 equals to W1 plus W2 plus W3 plus W4. Okay, just you add all the heat transfer. Okay, the heat transfer equals to the total work transfer. Just you add the heat transfer. That is plus 14.7 minus 25.2 minus 35.6 plus 31.5. You are having 17.44 kilojoule is the net heat transfer. And in a cyclic process, the net heat transfer and net work transfer are same. Hence, 14.744 kilojoule is the net amount of the heat transfer. At the same time, it is the net amount of the work transfer also, because in a cyclic process, summation of heat transfer is equals to the summation of work transfer. Okay, it is a simple process. As I said, Q minus W equals to delta E, and cyclic integral of dq equals to cyclic integral of dw. This you should remember for a cyclic process. Okay, now you consider the second problem. Okay. First, I am solving the simple problems. Try to understand. Okay, nothing is there plus and minus, but you should be very careful in sign convention. Okay, whenever heat added to the system, you have to take positive. Whenever the heat is transferred from the system, you have to take negative. W work done on the system is negative. Work done by the system is positive. These are the sign convention you should remember. Suppose if you are doing plus and minus wrong, so your entire problem will become wrong, because it is, even though it is a very simple process, but everything is depends upon the sign convention. Okay, second one, once again you see, you have to read the heading of the problem. Consider a cyclic process in a closed system which includes three heat interaction, namely Q1 is plus 20 kilojoule. Plus 20 means what? The heat is added to the system. Q2 is minus 6 kilojoule. Minus indicates the heat rejection from the system. Q3 is once again minus 4 kilojoules. That is the heat transfer from the system. And two interactions they have given. So W1 is 4,500 Newton meter. Newton meter means nothing but joules. Compute the magnitude of the second work interaction W2 in Newton meter. You remember 1 Newton meter equals to 1 joule. They have given all the heat transfer in kilojoules, but work done they have given in 4,500 joules. So you have to convert in kilojoules. You have to maintain the same unit. You have to express in kilojoules only. That is how you are getting kilojoules. 4,500 divided by 1,000. Okay, means you'll get 4.5 kilojoules W1. Okay. Next step you have to write. Okay. First you have to always write, for a closed system undergoing a cyclic process, cyclic integral of dq equals to cyclic integral of dw. That is q1 plus q2 plus q3 plus q4 equals to w1 plus w2. Okay, there are 4 heat transfer and 3 heat transfer and only 2 work transfer. Okay, so q1 is otherwise you can put it in joules also, or you can maintain kilojoules also, no problem, but you have to maintain the same unit on RHS side and LHS side. Okay, so here 20 kilojoules converted into joules, that is 20 into 1000, 20,000 joules. Minus 6, minus means whatever their magnitude given, same thing you have to take, minus 6 kilojoules is nothing but 6,000 joules. Minus 4 kilojoules is nothing but minus 4,000 joules. You remember 1 joule equals to 1 Newton meter. This is the LHS, summation of heat equals to summation of work transfer. Okay, 4,500 W1 is given, that is plus, you put as it is, and W2 we don't know. Okay, so just you simplify. So after simplification, we will get W2 as 5,500 Newton meter. Okay, because they asked you have to express magnitude in terms of Newton meter. So W2 is 5,500 Newton meter or 5,500 joules or 5.5 kilojoules. Once again, say magnitude is positive. The positive sign indicates that the work is done by the system. So this is the second problem. Third problem you see, okay. Third problem, a domestic refrigerator is loaded with food and the door closed. During a certain period, the machine consumes 1 kilowatt hour of energy and the internal energy of the system drops by 5000 kilojoules. Find the net heat transfer for the system. Okay. So here work done is given, that is 1 kilowatt hour. Okay. So 1 kilowatt hour is minus work done on the system. Okay, work done on the system is during a period the machine consumes. You see, consume means what? The work done on the system. That's why you have to take minus kilowatt hour. Okay, multiply by 3600 because we are going to express work done in kilojoule unit. So that multiply by 3600. Okay, so minus 1 into 3600 kilojoules. Okay, don't put like this 1 kilowatt hour as it is because you have to convert in terms of kilowatts. You have to multiply by 3600. That is 60 into 60. Next term U2 minus U1. Okay, U2 minus U1 is internal energy of the system drops. You see, gains means you have to take plus. Drops means you have to take minus. That is U2 minus U1. It is nothing but delta U. Delta U or U2 minus U1 equals to minus 5000 kilojoules from first law of thermodynamics. Then you apply the first law of thermodynamics. Q1 to 2 equals to delta U. Delta U is nothing but U2 minus U1 plus W1 to 2. As I said, Q minus W equals to delta U. Or we can write Q equals to delta U plus W1. Delta U is nothing but U2 minus U1. Now you substitute the given values. U2 minus U1 is minus 5000 and U1 is minus 3600. Okay, the U2 minus U1. You will get minus 8600 kilojoules. Once again, sign convention is most important. So the Q we are getting it as negative magnitude. Okay, that is minus 8600 kilojoules or suppose you are going to express in terms of megajoules, you can write minus 8.6 megajoules. 8600 divided by 1000, that gives your megajoule. Okay. So because sometimes they may ask express the heat transfer in megajoules. So in that case, you have to write this unit. Okay. So before solving any problem, so sign convention is most important. Okay. Suppose if you are U2 minus you are taking your positive, your entire problem becomes wrong. As I said, even plus and sign minus sign plays very important role in thermodynamics. Even though solution is only one line, suppose if you make mistake in taking the sign, and so your problem becomes wrong. So that's why be careful in taking the magnitudes. Magnitudes play very important. That's why every class I used to tell you have to keep remember certain things, certain concepts. Okay, especially sign conventions, then units. Okay, units are most important. Okay, the Newton meter. Sometimes they are going to give kilojoules. Some units they are in joules like that. But you have to convert them properly, and you have to take the same units throughout the problem. Then only the problem becomes correct. Okay. Okay, understood this problem? Any doubt? Okay. So today I explained simple problems. Tomorrow I am explaining a little bit complicated problem. Okay. Understood any doubt in this problem? Okay. Yeah. Hope you understood the problems. Tomorrow, I'll discuss some more problems. Okay. Any doubts, guys? First law of thermodynamics.
No, sir.
Good. Okay. So tomorrow I'll explain one more important problem. So try to attend all the class. Suppose if you miss one class also, you'll not able to understand the concepts. Okay. That's why try to attend all the classes regularly without fail. Then only you come to know. Okay. So all the subjects you can read by yourself, but thermodynamics is like not like that. You have to understand the concepts. Okay. Thank you one and all for joining. So I'll stop the session now.